Welcome, everybody. We're taking a look at section 6.1, where we're going to be learning about some properties and attributes of polygons. What I'd like for you to do right now, go ahead and pause the video and take a look at these pictures here of some examples of polygons, some non-examples of polygons, and to try to determine, based on these pictures, what you feel like some of the properties of polygons are. I'll kind of summarize my thoughts here in a minute, but go ahead and pause and do that. All right, welcome back. We're going to go ahead and talk about some of the properties of polygons. So I'm going to start by looking at the non-examples and try to figure out what makes that not a polygon. And hopefully by doing so, we can identify some of the things that are some of the properties that make something a polygon. So here we have this figure. We're going to start with this one. Actually, these two have quite a bit in common here. What I noticed about these two figures that I think are different than the rest of these is that these appear to be three-dimensional, right? They have some depth to them, right? If you kind of view it here, it's going out in depth. It's drawn on a flat surface on a piece of paper, but it appears to be a three-dimensional figure. That makes it not a polygon. Same thing with this one. Both of these appear to be 3D. Whereas everything over here, all of these polygons are two-dimensional. So that's going to be the first thing that I write down here. Two-dimensional. There's another term we use that in math. We say that it's a plane figure. It can be drawn on a plane, or it's contained completely inside of a singular plane. All right, let's go ahead and take a look at some of these other ones. These two figures right here and right here both kind of illustrate a somewhat similar idea about what makes something not a polygon. Neither of these two things are going to be considered closed. There's not a clear inside or an outside. Now, with this line, it's obvious that there's not really an inside or an outside. It's just a singular line. Whereas on this one, you'll notice, right, there's this sort of gap here, and it's kind of unclear about where the inside and the outside of the figure begins or ends or whatever. Whereas all of these shapes over here, you'll notice all of the vertices do actually meet each other and they're closed, and there's kind of a clear inside and an outside of the shape. So these are, I'm going to say open, whereas a polygon should be closed, so closed. So what I mean by closed, again, is there's sort of a clear inside and an outside. Couple more properties here. I'm going to go ahead and take a look at this figure right here and this one right here. And what I notice about them immediately is that they have some curved sides, right? Sides that are maybe circular arcs or just curves in general. That's different than all of these other ones, right? All of these that are polygons have only straight sides, right? So straight sides. Actually, this one right here, this three-dimensional shape also falls into this category of having some curves as well. And then finally, we have our last one that I haven't drawn any arrows to. And the reason I'm saving this one for last is actually some people consider this to be a polygon. I believe our textbook does not, but some people can consider shapes like this to be called what's called a complex polygon. In this case, it kind of looks like two of the sides actually intersect each other. So for our definition and the way that our book treats it, we're going to say that it's non-self-intersecting. I'm not actually going to add that to the definition because, again, some people call these complex polygons. We're not really going to work with them in this class, but it's kind of worthwhile just to know that they exist and to kind of have that conversation. Again, I'm not going to add that to the definition that we write down, but it's something to think about, and our textbook does not include those as polygons. All right, let's go ahead and move down and look at this definition that I wrote down. So a closed plane figure, two-dimensional, that's bounded by straight lines. Now, what precisely is the polygon? Is it the line segments? Is it the inside? What is it? And kind of the answer is all of those things. In some applications, we'll think about it as the line segments that bound the shape. And in some cases, we'll think about it as the area inside of it. And sometimes it'll just be all of that put together. So, they kind of all match that. Here we have a polygon pictured along with a couple more vocabulary terms. We have a side here. We have this vertex, and we have a diagonal. This diagonal references this line segment here. Yeah, these are some other vocabulary terms that are associated with polygons. We'll take a look at some definitions of those. In fact, I'll just get them all on the screen here so we can talk about them. So a side is simply a line segment, and all of those line segments form the perimeter of the polygon. Now, technically, these lines can extend. So we could have a line that contains the segment, for instance, AB up here, if I just sort of extend that out. And that would be fine. Parts of this are not part of the polygon itself, right? Polygon sort of starts and stops here at these vertice points that are there. But, there is a line segment in there that's part of our polygon, but the whole line is not. Anyway, and these are sides. Sides are simply line segments. Oops, I accidentally went over that. That's not a side, that's a diagonal. A vertex, or the plural of that is vertice. You see it right here, vertices. That's the plural form of this. So a vertex is a point where the sides of a polygon intersect. These are all points. You may not see a dot represented there, but where they intersect, oftentimes we'll label that with a letter if needed to represent it being a point. And then the last thing, a diagonal. A diagonal connects two non-adjacent vertices, and it's also a line segment. It's not curved at all. It is a line segment, straight line, part of a straight line. And it's important that we add in this term non-adjacent. An adjacent vertex would be like B and C. They're next to each other as you sort of go around the perimeter of the figure. BC, that would be connecting adjacent vertices. That's actually a side, not a diagonal. So here we have a picture of a diagonal from B to D. So that is non-adjacent vertices that are being connected. And there's a lot of vertices, right? We could connect any two of these vertices that are not adjacent and create a new diagonal. Let's go ahead and move forward. We're going to take a look at some further definitions of some characteristics of polygons. I've already sort of written some of this stuff out. So first of all, we have concave. And so we'll try to take a look at that picture here. I'm going to kind of describe it as being caved in. So this right here is our polygon, this shape. And what you want to notice about a concave polygon is it kind of has these indentions. That was what I mean by caved in. It could have one or multiple of those. To be precise mathematically, we need to think of some characteristics that always apply to concave polygons. And so one of those is that at least one of the diagonals contains some of the exterior of the polygon. So at least one of the diagonals is on the outside. And so you notice here, this diagonal connecting these vertices is actually entirely on the outside. That's one characteristic of concave polygons. Another one is this angle here, right? The angle formed at this vertex is actually greater than 180 degrees. It's more than a straight line. And that's another characteristic of concave polygons. So if either of those two things happen to be true about a polygon, we can call that concave. The next term we have is convex. Convex, one way to think about it is the opposite of concave. It doesn't have any of these caving in points. Another couple ways of thinking about it would be that all of the diagonals, you can see those drawn in there as red lines. All the diagonals are completely on the inside and the interior of the polygon. There's no diagonal on the outside. And the other thing is all of our interior angles here are less than 180 degrees. And all of that is true about all convex polygons. So another thing to make sure we understand is that every polygon is either concave or convex. However, there's a little bit of a confusion about this one, the triangle. is a triangle concave, convex? I like to think about it as convex. I think that all triangles are convex. But the reason that it's a little confusing is where are the diagonals? Where are the diagonals of a polygon or of a triangle? There aren't any. Every vertex is adjacent to another one, so there's no way to draw in a diagonal. So it doesn't really sort of fit either of the diagonal definitions, but it definitely fits this angle definition. So I'm going to consider it convex. Okay, so concave versus convex, that's one way to characterize a polygon. Another way to characterize a polygon is regular and irregular. So a regular polygon, you can see a picture of it here, has all congruent sides and all congruent angles. So both of those two characteristics. Only one of them is not enough to consider it regular. For instance, a rectangle is not regular necessarily, because it won't necessarily be true that all the sides are congruent. Irregular, again, irregular is the opposite of regular. So if a polygon is not regular, we call it irregular. And it basically just means that not all of the angles or not all of the sides or both are congruent. So, that could mean that only one angle is different than all the others. That's enough to make it irregular. Or one of the sides is different than the others, right? That's enough to make it irregular. For instance, like I just talked about before, a rectangle is irregular. Even though all the angles are congruent, most rectangles have two different side lengths, right? Making it irregular. And so you can see here, we have an irregular shape. This is a five-sided shape, a pentagon, an irregular pentagon. All right, couple more little details here. I'm going to cover these up real quick. We're going to make some pictures of a regular quadrilateral, I'm just going to leave a concave hexagon and an irregular octagon. We like to name the polygons based on the number of sides that they have. That's like kind of the generic naming. So we have triangles, quadrilaterals, pentagons, hexagons, heptagons, octagons, nonagons, decagons. We skip over 11. Some people call those undecagons, 12-sided shape, dodecagon. And then for everything else, we're just going to use an n-gon, where n represents the number of sides. So for example, if we had a polygon with 15 sides, we'd call that a 15-gon. Kind of sad, but that's what we do. Here we have some examples of some polygons with these different characteristics we've been discussing. So a regular quadrilateral, regular meaning all of the angles and all the sides are congruent. Quadrilateral means it has 4 sides. That makes it a square. Has all 90-degree angles, all congruent sides, it's a square. We're going to be spending a fair amount of time studying quadrilaterals in the future sections of this book, so that's why I kind of wanted to highlight that. A concave hexagon, remember concave means that one of the diagonals is on the inside or it's sort of caved in. Here we have sort of this indentation, and you'll notice, right, this diagonal is completely on the outside or in the exterior of the polygon. And this angle exceeds 180 degrees, right? It's greater than a straight line. So both of those things making it concave. And the last thing, an irregular octagon. Irregular just means that either all of the angles or all of the sides are not congruent. In this case, a lot of the sides are the same, but we have a couple that are different than some of the, 2 different side lengths that are used here. So that's enough for it to be irregular. And then an octagon means we have 8 sides. So 1, 2, 3, 4, 5, 6, 7, 8, like a stop sign, right? This could be drawn in many other ways, the same as this one, right? There's a lot of different options if you were just trying to sketch those out. Feel free to pause it and draw your own. That's actually going to be it for part 1. I will see you guys in part 2 of this.